Yeah. That's not right. That's not right.
I got set up for a board.
This is your chance to, suck up information. This is your chance. Your brains are plastic. Your brains are sponges right now. And you can absorb information the fastest right now.
This time of day or like this time of our lives?
This time of your lives.
Oh.
If you wait, in another 10 years, you notice it's slower. Another 10 years after that, a lot harder. It's harder and harder to absorb information. So just absorb it now. Don't waste your time, relations and stuff.
Yes.
That's what I've been saying.
Sorry, we can't date on absorbing information.
Exactly.
Is that what you tell your kids?
I'm unavailable.
You can date after your rate of absorption decreases.
Your brain is a plastic.
You can always date after your rate of absorption decreases. Plenty of time.
Oh, yeah.
Okay. Actually, I don't know if that's good advice.
Should we write it down?
To be honest, I'm not sure if that was a good idea. Okay. Okay. Let's go. So 6.4. 6.4 Hermitian matrices. So from here on in, we're actually going to allow our numbers to be complex numbers. Okay. So see the complex numbers. Right. So one typically uses Henry.
Last class we said we were going to go over one of the definitions of diagonalization. And one of it is if A is not diagonal, we call it defective. We only went over the say lambda is a root of determinant.
Oh, if A is no. Good call.
Oh.
Yeah. I don't actually know if I understood the right one. Oh, yeah, sorry, just if A is not potent. I was reading the wrong one.
Oh, we'll do that some other time.
Okay, sounds good.
Yeah. No. Okay. So complex numbers. So Z. One usually uses this sort of notation when you're using complex numbers. Use Z or you know how you use X and Y for real numbers. One often uses Z and W for the complex numbers. A and B are the real part, right? So the real part, right? This is usually written real part of Z, and then the imaginary part of Z. Right? A and B are the real and imaginary parts. And you have a graph. And here's the real axis. Here's the imaginary axis. Right? A plus BI. Right? Here is I. Right? So you have A here, and then BI here. A plus BI. Okay. Okay. So complex numbers, you have Z equals A plus BI. And we have this thing, Z bar, which is defined as A minus BI. Okay, so if Z is A plus BI, then Z bar is A minus BI. And this thing is, Z bar is called the complex conjugate of Z. Complex conjugate. Okay, and you see what that corresponds to graphically, right? If this is A plus BI, if Z is A plus BI, then Z bar is the reflection across the real axis, right? The reflection across the real axis of Z. Okay. Okay, so that's the first definition. Second definition, one has this thing called the modulus of Z. but all that is the norm of z. Okay, and so that's going to be the square root of z bar times z, right? Z bar times z, which, if you work it out, is the same thing as a squared plus b squared, the square root of a squared plus b squared. Right? Because you have, right, a minus bi, a plus bi, right? So you're going to get a squared minus bi squared. Right? A squared minus bi squared is the same thing as a squared plus b squared. Right? Z bar is a squared plus b squared. Okay. So one calls the norm of the absolute value of z when you're in the complex plane, one uses this term modulus, but it doesn't really matter. You can call it the absolute value if you feel like. Okay. Okay. So we are going to be talking about Cn. So Cn is going to be, these vectors z, where you have z1, z2 to zn, right? And each of these guys, each of the zi's is a complex number. Any question?
Can we open the door?
Oh, yeah.
Goes to the long sleeve, it's just a terrible idea.
Okay. So Cn is what you think it is, right? It's just, n copies of C, right? Just like Rn is n copies of R. Okay. And just like we define the complex conjugate, you can take a complex vector and take its complex conjugate, right? It's just going to be the vector of complex conjugates. Okay. And just like we defined, yes?
So z bar is the same as.
It's going to be the same as z, but with complex conjugates of
Oh.
each thing.
Okay.
So you take you have a complex vector, and you just take each of these things is a complex coordinate. You take the conjugates of all those coordinates. Okay. We define the magnitude of a complex vector by taking the complex conjugate, transposing it, and multiplying it by z 1/2. So you use matrix multiplication. Right? So what this works out to be is z1, z2 bar, z1 bar, z2 bar, to zn bar against z1 down to zn, everything to the 1/2. And if you work it out, you see that you get the modulus, the sum of the squares of the moduli to the 1/2. Okay, and the book uses this notation. Instead of writing z conjugate transpose, it writes z super h, okay. Which is non-standard, but it'll be actually kind of convenient. Non-standard, but convenient. So z conjugate transpose, we abbreviate with an h. Okay, going on, more notation. We can define a complex inner product Cn by the inner product of two vectors we define to be the conjugate transpose of the second times the first. Yeah.
This is just a random question. Why do we have the little two dots before the equal signs?
That means define the equation. So we're introducing this thing. What does it mean? We're going to define this as this. This is the definition of that.
Okay.
Okay. If I said like this equals that, it could just mean that those things are equal to each other, right? But this is actually the definition of it.
Okay. Thank you.
Okay. Okay. So so you do need to check that this is an inner product. And when you do, you'll notice something funny. What happens when you take a complex number, alpha, and you scale the second guy by it?
It's not complex.
Well, let's see. So if we use the definition, we're going to get AW conjugate transpose, right, times Z. Right. So, right, what are you hoping? What should happen? Right, if you scale the second vector by multiplying each of the components by some number. Right. Think back to your old dot product. Right. In Rn, if you take a vector and you multiply it, you multiply the second vector by some scalar. What do you get?
Scalar.
You just get the scalar times the dot product. Right. The dot product is linear. Right? The dot product is linear in each variable. But what happens when you do that here? We multiply by multiply the second vector by some complex number. What do you see happens? Do we get alpha times the inner product of Z against W? Is that what you get? No. What do you get?
You get the complex conjugate.
Yeah, you get the complex conjugate, right? So it's actually not linear. This isn't an inner product. Okay, it's not an inner product because in the second variable, it's not linear. It's what's called conjugate linear. Okay, so this inner product is conjugate linear in the second variable. So it's not what we called an inner product earlier. It's something a little bit different, what we call a complex inner product. Okay, so that's why I put the word complex here. It's not really an inner product. It's not a real inner product, it's a complex inner product. Okay. But what happens if we multiply by the first variable by alpha?
We're good.
We're good. It actually is linear in the first, right? It's linear in the first variable, but conjugate linear in the second, right? Because you multiply Z by alpha, right? You just get an alpha here, right? That alpha pulls out, you get alpha times the dot product, times the inner product, right? So it's linear in the first variable and conjugate linear in the second variable.
And that's for alpha being a complex number, right?
Yeah, alpha is complex. Yeah, so notice if alpha is a complex number, then blah, 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 blah. But that's okay. It's still a kind of inner product. It's just a complex inner product. Okay. Okay. Complex matrices. So you're going to have n by n matrices that consist of complex numbers. So just like before, well, as you might expect, right? If you have a matrix that's a complex matrix, then we define the conjugate, the complex conjugate of that matrix, in the way that you would think. Right? You're just going to conjugate. You take conjugates of every variable. The conjugate matrix by taking conjugate, by conjugating each variable. I'm sorry, each entry. Okay. And here's the definition that will be very important for us today. If M equals n conjugate transpose, we call M a Hermitian matrix. Okay. We call M a Hermitian matrix. And again, I think the book uses this notation, M super H. And now you see why there's an H. It's for the word Hermitian. Hermitian is from the mathematician Hermite. So just think about it. If M is a real matrix, then what is this saying? If M is a real matrix, such that it's equal to its conjugate transpose, what is that saying about your matrix? Your matrix is symmetric, right? So this is some sort of complex analog of a symmetric matrix. So for example, if I have this matrix, 1, 3 plus I, 3 minus I, 0, this guy is Hermitian. Okay. And here's an exercise for you to do right now. ZAW AZW. Show that if A is Hermitian, then this holds true. Yeah, Mia.
In complex matrices, oh wait, never mind. How do you find the complex conjugate of a real number?
You take the negative of its imaginary part, but it doesn't have an imaginary part,
So it's just the
nothing
same.
happens.
Okay.
Yeah, or to think of it geometrically, right? You're taking the reflection across the real axis, but you're already on the real axis, so
Okay.
you reflect, nothing happens to you.
Okay.
Okay, so take 30 seconds and write down, clarify to yourself that this is true. Right. Okay, turn to somebody next to you and say, it's clearly true. Okay, right. So why is it true? Well, if you take you take this thing, then the definition of this is that you take A, W, H times Z, right? But A, W, H times Z is the same thing as, right, you're taking the conjugate transpose. So this is going to be right, AW conjugate transpose. But the transpose of this is going to be a product of transposes is going to be the product of transposes in the reverse direction. Right? Right. And so, and then, right, A is Hermitian, so you know that A conjugate transpose is the same thing as A. Right? And so you get AZ W. Okay, any questions? Okay. Okay, let me start over. Let me go back here because we're going to use the whole board. It's so theorem. A complex square matrix. Let's say A is Hermitian. If A is Hermitian, then all eigenvalues of A are real. 2, eigenvectors corresponding to distinct eigenvalues are orthogonal. Maybe I'll let you think about it. These are actually pretty easy to see. See if you can figure it out. Take a minute, take a couple minutes, and see if you can see that all the eigenvalues of A have to be real. And the hint will be to use the fact that we've just demonstrated, that if you have a Hermitian matrix, then Hermitian matrix is such that you can switch it over to the other side of the inner product. Okay, so here's a further hint. Consider A, B, V, where V is an eigenvalue. Maybe I should have had you do the second part first, because that would should have prompted first. Okay, let's take a look at it. Okay, so say that V is an eigenvector corresponding to eigenvalue lambda, and let's consider AV, the inner product of AV against V. Okay. Well, by what we just saw, because our matrix is Hermitian, we can move the A to the other side, right? By this thing, we can move the A to the other side, right? And so this thing we're going to get lambda V V here, and over here we're going to get V lambda V, right? So what? So what? Mia.
It has to be real because otherwise it's like a complex conjugate of itself.
Exactly. Right. So, right, we know that the inner product is linear in the first variable and conjugate linear in the second variable. Right. It's linear in the first variable, conjugate linear in the second variable. So that tells us that, you know, lambda, right, V is a non-zero vector. So we cancel off, we can divide by the magnitude on V on both sides, and we see that lambda must equal its complex conjugate, right? Well, the only numbers who equal their complex conjugate are real numbers, right? Because if you reflect it, if it's not real and you reflect it, you get something different. Okay. Number two, you do something similar. Let's say that V1 is in E lambda 1 and V2 is in E lambda 2. And again, we consider the inner product of one guy against the other guy, and hit one guy with the matrix. Okay? Again, we get E V1 A V2. See what happens, right? We're going to get lambda 1 V1 V2 equals V1 lambda V2. It's lambda 2 V2. Right? But so what happens then? What do you see happens? What do you see happens? Well, this is going to be what? This is going to be lambda 1, V1, V2, right? And this thing is going to be lambda 2, V1, V2, right? Why isn't it conjugate?
Because it's real.
Because it's real. Right. It is conjugated. Right. Okay. And we are given that lambda 1 and lambda 2 are not the same, right? Lambda 1 and lambda 2 are not the same. And so what does that tell us? That tells us that v1 and v2 had better be 0. Right. Because if it's not 0, we get that lambda 1, lambda 2 are the same. Okay. So the eigenspaces are perpendicular to each other. The eigenspaces are perpendicular to each other. Right? So that's pretty cool. Right? Whenever you have a Hermitian matrix, then you look at the eigenspaces, and they are all perpendicular to each other. Right? They're all perpendicular to each other. So you're thinking, well, okay. There's a corollary of this. Corollary. If A is sort of the obvious corollary. If A is Hermitian and has distinct eigenvalues, A is Hermitian and has distinct eigenvalues, then what's going to happen?
The vectors are going to.
Okay, certainly, right? Then we can get an eigenvector basis. It's going to be diagonalizable, right? Certainly that we could say that, but we could have said that before, right? Because we already had the fact that if any matrix has distinct eigenvalues, any matrix with distinct eigenvalues is going to be diagonalizable, right? What we have is something a little bit better, right? Not only do we get an eigenvector basis, right? So remember, right? If we had distinct eigenvalues, that guaranteed us an eigenvector basis, and that guaranteed us that the matrix was diagonalizable, right? And now we have something even better. That further, the eigenvectors are all perpendicular to each other, right? The eigenvectors are all orthogonal to each other. So not only is your matrix that you use to your basis matrix, not only is it all eigenvectors, but further they're perpendicular to each other. Okay, so so we just say that then there exists an orthonormal matrix. An orthonormal matrix that diagonalizes A. Okay, and the proof is just what we just said. That you say, well, look, A has n distinct eigenvalues. Means that it has n orthogonal eigenvectors. So then normalize them. And let so you get these vectors u1 through un, which are an orthonormal eigenvector basis, orthonormal basis of eigenvectors. Then the matrix U that you make out of these guys diagonalizes A. Okay, so this is not that much more than what we said previously, right? We already knew that if you have n distinct eigenvalues, you get an eigenvector basis, and then you can diagonalize using that eigenvector basis. The only thing is that here, since our matrix is Hermitian, we know that these guys are in fact orthogonal to each other, and so we can also normalize them and get an orthonormal. We get diagonalized by an orthonormal matrix. Okay. Now, I should say that this is orthonormal with respect to the complex inner product, and so one doesn't call this an orthonormal matrix. It's actually what's called a unitary matrix. So a unitary matrix means U is unitary if, right? So U is a n by n complex matrix if its columns form an orthonormal set. Orthonormal set with respect to the complex inner product. Right. With respect to the complex inner product, not the old inner product. Okay. So the thing is that it's a complex matrix, right? You're gonna use the complex inner product. All the guys are orthogonal with respect to the complex inner product, not the real inner product. And so we have a different name for these guys. But basically, you think of unitary as being the same thing as orthonormal. Okay, it's just the complex version of orthonormal. Okay. Yeah. So I should call this the definition. Definition. U is unitary if its columns form an orthonormal set with respect to the complex inner product. One remark is that what unitary means is that U conjugate transpose, U is the identity matrix. In other words, that U inverse is UH. That UH is U inverse. So the conjugate, if you have a matrix and its conjugate transpose is its inverse, then that's a unitary matrix. So rewriting the corollary, using this language, if A is Hermitian and has n distinct eigenvalues, then A is unitarily diagonalizable. In other words, there exists a unitary matrix U such that U inverse AU is diagonal. Okay, so if A is Hermitian and has n distinct eigenvalues, not only are you diagonalizable, but you're unitarily diagonalizable, something better than just being diagonalizable. Okay. In fact, something far more remarkable, is true. And this is what we'll see next time. It's called the Spectral Theorem. The Spectral Theorem for Hermitian Matrices. If A is Hermitian, then A is unitarily diagonalizable. Okay, so you don't need to know anything about the, even if A doesn't have n distinct eigenvalues, something nice still happens. You're still able to diagonalize it. Okay, right? The n distinct eigenvalues, what that guaranteed was that you would have these one-dimensional eigenspaces. You had n one-dimensional eigenspaces, right? And basically that guaranteed that you could take Rn and write it as this direct sum of orthogonal, like one-dimensional orthogonal one-dimensional guys. Okay, and what this is saying, what the spectral theorem is saying, is that that's going to happen whenever your matrix is Hermitian. That is, whenever your matrix is Hermitian, then your eigenspaces are going to be enough to fill out all of Rn. Right? The geometric multiplicities will all be equal to the algebraic multiplicities, and the sum of all those dimensions of the eigenspaces will be n. Okay. And since these guys are all perpendicular to each other, what you have is a way of splitting Rn into a direct sum of orthogonal subspaces. Okay. That's really what this theorem is about. Taking your space and splitting it up into a direct sum of orthogonal subspaces, each of which is preserved by A. Don't worry if you didn't understand what I just said. Okay, it's okay.
Okay.
Yeah, but that's what's going on. Okay, that's what's going on, right? Each of these spaces is an eigenspace, right? But when you hit it with the matrix, it doesn't move, right? The subspace is doesn't rotate or anything, right? Everybody in it, if you hit it with the matrix, it just still stays in it, right? Right? They just get stretched. This is what the term is called invariant. The subspace is invariant under the matrix. Okay. And so what this is saying is that you can